they will catch up. So good afternoon, everyone. Welcome to this August mini-school of the National Institute for Theoretical and Computational Sciences. My name is Francesco Petruccione, and I'm currently the interim director of NITheCS. Today, it is my pleasure to introduce a team of the WITS School of Physics that kindly offered to introduce us to the use of big data and machine learning for particle physics. Yeah? And the team of lecturers is headed, if I can say so, by Professor Bruce Mellado, who is a full professor at WITS, and he's also a senior researcher at the Temba Labs, and is also the director of the Institute for Collider Particle Physics, among many other duties that he has. In particular, recently, during these times of the COVID pandemic, he played a major role in the Gauteng committee that protected us from COVID. So thank you very much for that, Bruce. And Professor Mellado, I mentioned there is a team of 3 lecturers for this mini-school, and I will ask now Professor Mellado to please introduce the speaker of today. That is Professor Deepak Kar, who is also based at WITS. So Bruce, if you would like to quickly introduce Professor Kar and maybe say a few words on the concept of the mini-school to prepare our audience for what is coming this month. Thank you very much.
Thanks, Francesco, for the kind introduction. So the idea of these mini schools in big data and machine learning, with emphasis on the symbiosis between big data and machine learning, came through interactions with the CHPC, where we had already organized a number of interactions and mini schools. We had done so for SIPE, and now we're very honored to be able to do that for NITheCS. So the way it is structured is that Professor Carr will give us an overview of machine learning in particle physics, with a basic classification of what machine learning is, different methodologies and algorithms. I will come in talking about the connection with big data, because machine learning is difficult to disentangle from big data in big sciences, like particle physics or SKA or whatever. And then Dr. Ruan will come in with a tutorial, the last 2 lectures. So it's basically a 3-part presentation. So it's a pleasure to introduce Professor Carr, who will tell you how many countries he's been to. He's got a record, he's almost got a Guinness record, and he will introduce himself much better than I can. All right, take it away, Deepak.
Thanks, Bruce. And Francisco, it's a pleasure to be here. Unfortunately, I can't see who are connected, but welcome all. Yeah, so as Bruce said, I am a physicist, but let me kind of step back and explain my career profile, which hopefully should be like motivating for some of you. So I grew up in Calcutta, India. That's the picture of my university campus on the right. After finishing my master's there, I moved to US, more specifically to University of Florida in Gainesville, where I did my PhD. Now that's a picture of a space shuttle launch in Kennedy Space Center, which is one of the main space shuttle launch sites in US. Now that picture was taken by me. It was, believe it or not, 3 a.m. at night, and we were like 10 kilometers away from across the river. And interestingly enough, I know most of you have studied physics, and you know that light travels faster than sound, but that was a live demonstration. We saw that flash first, and then the sound came like a few seconds later. From there, I obtained my PhD, and then I moved to Dresden, Germany, where I did my postdoc. It's typical in our field to do multiple postdocs. I spent a year in CERN, Geneva, because that's where our lab is. We'll talk more about that as we go on. Then I spent a few years in Glasgow doing another postdoc. And then in 2015, I landed up in Johannesburg. And as I keep saying, it has been a nice ride so far. And I have not been like mugged, shot at. I'm still alive, so I think that's good. Right. Now, before we start, lot of things, a lot of the topics I would discuss, in fact, a lot of the physics, even the machine learning part I discuss, is from my book. So this is the book I wrote based on the honors course I started in WITS on particle physics. So when I started this course, there was no book. So I kind of had my own lecture notes, which evolved to a book which was published by Institute of Physics in UK. It's one of the first books talking about the stuff we do at the LHC. So I have linked, I'll send around the link, or I'll have the slides, so you will have the link. But if you can't access it, send me an email. We'll see what we can do. Now, before we get started, I'm just going to emphasize a few points. I'm a physicist. I'm not a computer scientist, so I don't develop machine learning algorithms, but we use them quite a lot. For me, it's mostly in particle physics problems. For Bruce, as Francisco mentioned, it's also in like real world modeling, which is no doubt is very important. For me, it's mostly looking at physics problems. Now, again, I don't know who you are, but I'm guessing you are enthusiastic about machine learning. That's why you are here. But many of you may be a bit more agnostic about the physics part. But of course, when you try to analyze data in whatever shape, you need to know what the data is coming from, what the data means. Because what I keep saying is the difference between a good machine learning, like a good data scientist, and a bad data scientist is not that they can't code. All of the data scientists can code and run Tensor Flow or Keras or scikit-learn, whatever. But some understand the data much better than the others. So we need to have some idea about the physics part. Of course, we can't cover entirety of the particle physics in 2 lectures. I'm not even going to try. But I will spend at least half of today's lecture on the stuff we do, and then I'll talk about how we use machine learning to solve those problems, to get better discrimination and whatnot. And we'll continue with that in the lecture next week. But before that, what are the big problems or the big questions we are trying to answer? Now, again, I'm sure you know our universe is made of elementary particles, they have the interactions. But we don't know why the particles have the certain properties, why they have certain mass, why they're like 3, I don't know, again. So we have like different particles and we classify them into generations. And each generation has there are like 3 generations of leptons and quarks. So why there are 3 generations? You probably heard of the Higgs boson discovery, which happened in 2012, which is like the one golden moment from LHC so far. Hopefully, first of many. But the Higgs boson mass, which we measured to be 125 GeV, that might ring a bell. And that number is actually something very interesting for us, because if the number was different, a lot of things in the universe would have gone wrong. I'm not going to go into technical details. It's essentially called a fine-tuning or hierarchy problem. So we want to know, like, is it an accident that Higgs mass is 125, or there are other particles which is contributing to it? Then there is this mysterious particles called neutrinos. They are very light, but they have some mass, and why they're the case, and they actually transform into each other. So why that's the case, all of that. One of the biggest mysteries now is the nature and existence of dark matter and dark energy. The visible matter, which you see all around us, is like 5%. Everything else is not something we know. From astronomical observations, we can say there is something out there. We don't know what that is. In fact, whenever we talk about dark matter to a general audience, not to physicists, not to people who have done any physics, they are like, why do you care? And I saw a very nice paper yesterday in Archive where people talk about, if you have dark energy, maybe you can harness it to have a clean energy solutions. And reduce load shedding in South Africa. That's a lot of wishful thinking, but yeah. So trying to find dark matter is a big part of LHC physics program. Then there are other things, why there is more matter than antimatter, blah, blah, blah. So we're not going to discuss that. But I just wanted to say, like, there are a lot of open questions in particle physics. Even after the discovery of Higgs boson, we have, as you may know, 4 different fundamental forces, but they have very different behavior. At least gravity is much weaker than everything else. Why is it so? We don't know. Is there a point at a very high energy regime where they meet? We don't know. So these are the things we do. And I really love this graphic, and I think this applies to every field of knowledge. There is a known things which we have found out over centuries. And then there are like things like known unknowns. For example, the Higgs boson, which was discovered in 2012, but it has been postulated in 1950s by a group of scientists. And we have been searching for that in colliders for many years, and we found it. So that's like a known unknown. We knew there has to be something like the Higgs boson. We didn't know the exact mass, but we knew it is there. And then for a scientist like me, the unknown is the most exciting part. So dark matter, as we talked about, is the known unknown. We know there has to be something. But then as scientists, sometimes we might discover something which no one expected. And that's the fun part. That's why we do science. I'm not going to, as I said, I can't introduce particle physics to you in 2 hours, but I'll just very quickly browse over some topics. So what happens is we have protons and protons collide inside a detector. We'll talk about a detector in a minute. But typically, every particle is denoted by what is called form momentum, and then there are particles which come out. They have their form momentum. So they're typically denoted by, if you have done some physics, energy, px, py, pz, or momentum in x, y, and z direction. Now, what happens is in the particle colliders, we'll talk about it later, but the z-axis is along the line where particles are coming from, so we are basically focused on the xy plane. Now, we use form momentum, and the reason I'm emphasizing this is when the particles come out of the collisions, and we'll see, a lot of particles come out when two protons collide. And when we say, like, we collect the data, that's essentially what we are trying to collect. We want to collect the form momentum of every single particle that's coming out of it. And that actually gives us all the information we need to do new physics. In fact, even in the machine learning algorithms, some of the crudest machine learning algorithms use just the form momentum of all the incoming particles. So that's why I wanted to introduce that term. It's just energy and the three momentum in some sense. And then there is a property that if you essentially do the scalar product of the form momentum itself, it's invariant, and it actually gives us mass. So if you have like a bunch of particles coming in and you calculate this thing, you get what we call invariant mass, which is interesting because if our collision produced a heavy particle, like the Higgs boson, and it decays into two particles, like two photons, and you calculate the invariant mass of the two photons, you get the mass of the Higgs boson, which is something we would use repeatedly when we talk about searches for new particles. So that's what I said. Now, why do we do this? What's our playground? We have this beautiful machine, which is called the Large Hadron Collider. It's in the Center for European Nuclear Research, or CERN, which is popularly known. If you have seen Angels and Demons or Dan Brown novels, you probably heard of CERN, even you might have seen some pictures. It's under a beautiful part of the world in French-Swiss border, surrounded by lakes and lovely snow-capped mountain peaks and whatnot. The actual ring is like a 27-kilometer in circumference underground, and protons are moved in the ring in opposite directions, and they are brought to collide at 4 different points underground. And when I say collisions, don't think of one collision. We have 40 millions of them in 1 second, so a lot of collision. And this affects the way we do things. Again, we'll come back to that. I just want to point out some things. And that's what the collision looks like, a firework. Two protons collide, and hundreds of particles come out. We have to somehow measure those things, because otherwise, what's the point? So we have this really complicated detector. We have 4 of them along the ring at different points, but we are going to focus on the Atlas, which is something Bruce and I and Xifeng works on. So it's a relatively large detector by the comparisons of other detectors at LHC. It has different layers, which detects different kinds of particles. We are not going to go into details, but the particles that come out are charged particles, neutral particles, electrons, photons, muons, and neutrino, which is the kind of like a ghost particle. So neutrinos don't interact with the detector. They just go straight through. And yeah, so these are those particles come out and the layers of the detector detects it. You can think of it as like a very sophisticated phone camera in some sense, just built-in layers. As you can see here, different layers are sensitive to different particles. So as I said, detectors measure particle trajectories because there is also a magnetic field. You probably know from your undergrad physics that magnetic field bends the path of charged particles. From that, we can measure the momentum and the charge from the direction of the bending. And from the information in the detector, we try to figure out what particles came out during a collision. There is another very interesting concept, which is called trigger, because I said like there are so many collisions. Now, our hardware, our detector, like the connections, the hardware is not equipped to, and even our storage is not equipped to save so many collisions. We just can't. It's impossible in terms of computing and bandwidth and whatnot. So what we try to do is we try to select interesting events. Now you might wonder, how do you know which event is interesting even before you looked at them? So what we try to see is, because if we are expecting a new particle, typically it has a lot high energy or a high mass, because if it had low energy, we probably would have seen it already. So our trigger system, again, without going into a lot of technical detail, tries to identify events which have like high energy deposit in parts of the detector and stuff like that. And it tries to save only those events, discarding the others which are potentially uninteresting. So as I said, there are a lot of particles coming out. Now electrons, muons, photons, we try to detect them like individually. But what we also have is a lot of quarks and gluons. If you heard of those things, quarks and gluons, these are elementary particles, but they have a very interesting property that you don't see free quarks and gluons in nature. They combine with other quarks and gluons and form something we call hadrons, which are like composite particles of quarks. So what we see in the detector, the charged hadrons and neutral hadrons. And what it happens is, if you look at the right-hand picture, from a collision, if you have a few quarks and gluons, each essentially gives rise to a large number of hadrons. So what we try to do is we try to collect all these hadrons coming from one quark or one gluon in conical objects called jets. Of course, that's a very hand-wavy argument. There are like actual mathematical algorithms, how we form jets, how we decide which particle enters which jet, and then we have like size of the jet, which we have to decide beforehand. But let's not go into that, but just remember that you have these conical things called jets. Interestingly enough, as I know, the name jets kind of came from this really beautiful water jet in Lake Geneva, which is right next to CERN. Jet d'eau, if pardon my French. so that's like a water jet, and from that they named these things particle jets. That's what I believe. And this is actually a real picture of jets coming out from the Atlas detector. So each of the bunches are one jet. As you can see, there are a lot of particles, a lot of hadrons bunched into different directions, and they are the jets. Now, why I'm talking about jets? Because I work a lot with machine learning with jets, which we'll cover in today and tomorrow. So that. Now, one of the things which I need to emphasize is we don't really see what's coming out of the collisions. For example, as I just said, you have quarks and gluons coming out, but you don't see quarks and gluons. You see hadrons, which we collect in jets. But even going beyond that, most particles have finite lifetime and they decay. For example, the Higgs boson again, which I keep saying because that's something which everyone is aware of. The Higgs boson doesn't hit your detector, and you don't say, oh, in my detector I found a Higgs. What you find is the decay product of the Higgs decaying into 2 photons, 2 electrons and 2 muons, 2 jets, whatnot. So our job is a bit challenging, and that's where I think machine learning would come in to find out, this is what I see in the detector, but did it come from a heavy particle? Did it come from a particle we know, like the Higgs, or the W boson, or the Z boson? Or it came from a new particle X? How do we find that out? And also, like, you have worked in labs, and nothing works perfectly. So all the detectors, even though we put incredible amount of effort in them, we have a nice team at WITS which works on a part of the Atlas detector called tile calorimeter. But even though we have these fantastic detectors, nothing is perfect. So there is some resolution effects. Some part of the hardware sometimes doesn't work. So we also have to account for those things. So that's why, as I said, we don't get what actually happens in the collisions. I think I'm going to skip that. I'm going to skip that as well. I'll very briefly describe the coordinates because we will going to use that as we move along. So as I said, the collision happens in Z plane, and only the transverse plane, XY, which is around the Z axis, essentially perpendicular to the Z axis, is relevant. So typically what we do is, I'll just skip that. So think of this cylinder as your detector. Detectors are roughly cylindrical. IP is where the collision happens. And rather than using XY, we use two coordinates called eta and phi, which are two angular coordinates. Phi is essentially the red thing which wraps around. So phi tells you like what the angle is. And then we have this thing called eta, which we call pseudo rapidity, or it's very close to what we call rapidity. It goes from, at the center of the detector is 0, and it goes from plus infinity to minus infinity, essentially. So every particle can be determined by two coordinates, eta and phi in angle. And yeah, that's pretty much it. So whenever we talk about jets, we talk about the particles inside the jets. We would say each particle is given by an eta and phi. So that's your XY coordinates in some sense in transverse plane. And one last bit before we go into the nitty-gritties of, no, we will talk about physics a bit more. But when you see data, I know when you do machine learning, everything is data, and that's fine. But when us, particle physicists, talk about data, we mean data collected from the machine, something which happened in nature. So that's data. Everything else we use is simulation. I'll explain what that is as we go along. But I know you use data. So just to make sure our terminology is correct. So that's what. Now, yeah, so we look at the data, but we want to see if there is something new and exciting lacking in the data. But you can't do it unless you have a reference. Because if your data is as expected from what we call the standard model, or what we expect from the existing knowledge, then you haven't really found anything new. But if your data deviates from the predictions, from the current theory, then you have something exciting. In order to know if it deviates from something, you need to have that something. That something is the reference, and we use simulation for that. Now, what happens is, because I told you, we produce hundreds of particles in every collision. So it's almost impossible to calculate everything. And also, if you have learned a bit of quantum mechanics, you know nature is probabilistic. So even if you do the exact same thing every single time, the outcome is different. So we use something called Monte Carlo methods. It's named after this famous gambling resort in French Riviera, I believe. And why is the connection with gambling? Because gambling is a matter of chance, luck, and Monte Carlo essentially uses probability, which is the same. So a very simple example, just to wrap our head around this Monte Carlo method, if you haven't, let's say you want to find the area of a circle. Sure, you would be like, why he's wasting time on that? We all know it's pi r squared. But let's say you don't. Let's say you have like a square and a circle, but you don't know the area. You know the area of the square, but you don't know the area of the circle. You don't know this pi r squared, you forgot. You woke up one morning forgetting all the formulas. So what you do is you take like a dart or a stone and throw it inside the square. And you keep a count where it hits. Does it hit inside the circle or is it hitting outside the circle? And then you take a ratio of the number of hits inside the circle by the number of hits inside the whole square. You know the area of the square, you take the ratio, and you get roughly the area of the circle. And the more times you throw the dart, better your approximation is. So that's what we do in LHC in some sense. We throw a dart following the constraints imposed by the particle physics. We know that particle, like even you know, like we have to conserve charge, you have to conserve spin, we have to conserve energy momentum, all of these things we have to factor in the simulation, but then we figure out what particles come out. We also have to figure out the other thing, which is, as I said, when we collide protons and protons, the outcome is not the same. So we know from theory, like how many times the Higgs boson may be produced, which is, I forgot the exact number, Bruce can correct me if I'm wrong, like it's probably like 1 in a million. So if you have million collisions, you will have 1 Higgs boson, like roughly. And you will have maybe 100 Z bosons and I don't know, 5,000 W bosons or 10,000 W bosons. So from theory, we know the fraction of different particles, but you can't say one event, this is what I'm getting. If you generate a million events, I should expect 1 Higgs or something like that. So that's also why we have to throw a dice, chance, Monte Carlo. This is a kind of a picture of how we simulate the whole event. There's a lot going on. I don't think we need that for this lecture, but just to understand the complexity of the process. There are so many different things going on in a collision. So that's roughly half of our lecture, which is fine. So where do we try to use ML or machine learning? So we do analysis with this data collected from the machine and the simulation. We try to extract physics information. And then we have two kind of things, measurements, which measure things like the mass of Higgs boson, and searches are designed to look for new physics or new signatures. Now, how do we do that? We have observables called charged particle tracks, jets, electrons, muons, photons, and this object called missing energy, MET, which essentially means if you have a neutrino, which essentially escaped the detector because neutrinos don't detect the detector. If you add up the 4 momentum of everything else, energy and momentum, from your first year physics, you would have an imbalance of momentum, and that's what we call missing transverse energy. From this, we can start with the 4 momentum of every particle that's come out, but that's messy, because if you have 100 particles coming out, that's like 400 variables. If you're a machine learning person, you can say, oh, 400 inputs, I can handle that. But typically, historically, we don't try to start with these 400 things. We try to make physics observables, like transverse momentum of the jets, which already combine many particles, or mass of some invariant mass of something. Because we are physicists, we have an intuition of what things we should look for. So a lot of times in particle and machine learning, we don't start with the 4 momentum of everything. We start with these observables. So I just wanted you to know that. And then there's the other concept, which is pretty much true for machine learning in general. A particle physics signal. So we are looking for a new physics signal, but we know it would have a specific final state. Maybe if we're looking for the Higgs, we know that it can decay into, let's say, two electrons and 2 muons. So maybe you're looking for Higgs in that particular channel. But that doesn't mean that 2 electrons and 2 muons cannot come from other processes. They can come from other processes, standard model processes. Typically, the cross-section of the standard model process would be higher. By that, I mean there'll be more standard model EE mu produced compared to the new physics case. So this is called background, which is the same or similar final state as the signal, but not quite, but not coming from the signal. So not something we care about. So the whole game is to apply cuts, apply selections on the observables to retain most of the signal and reject most of the background. And this is the game we play in science, in many branches of science. You want to collect your signal, reject your background. This is done by what we call object and event selection. So essentially what we mean is we apply a specific trigger. I explain what a trigger is to select the important or the events which have the right final state. From simulation, we know we are looking for this new physics signature. So these are certain physics properties of jets, missing energy, blah, blah, blah. So we do that. And then we apply some selections on those. We calculate what we call significance, which is generally given by S over S, square root of S over S plus B. So S is number of signal events, B is number of background events. The larger this number is, your chances of discovering that signal is higher. If this number is really small, that means your signal is like buried under the background and you are searching in darkness. There are different kinds of backgrounds. I don't think I'm going to go into that. So irreducible means the exact same final state. Reducible means similar final state. Now you may ask why that's important, because again, we are dealing with detectors which have finite object recognition capabilities. So it might misrecognize an electron as a jet or a jet as an electron. So even if you're looking at mu mu E final state, maybe you end up with mu mu E and a jet, and you accidentally thought that jet is an electron. So that would also be a background. And then we have something called combinatorial, which essentially means that you have maybe you're looking for mu mu E, but maybe there are other muons coming from something else, and you pick the wrong combination. So all of these, which we have to now we resolve them manually, or mostly we have resolved them manually, but now we're using more machine learning techniques to discriminate these backgrounds, as we'll see. Oh, I'll explain one thing, because we will use this a lot in machine learning and everything else, which is called ROC curves. So these are called receiver operating characteristics. These are used a lot in engineering, but these essentially tells you signal and background discrimination. So let's see. So on the left-hand side, forget about the specific details, but we have a signal and a background. The red points, let's say, is a signal distribution, and the black points are the background distribution. And you want to see how well you can separate signal over background. If you put a cut on a certain value, so if you say I'm only taking events or only taking these data points where the value of this variable, whatever that may be, is over 0.8, then you definitely get more signal, you'll get some background. But how do we quantify that? So we scan over the full range, and at each point, we try to calculate the signal, what fraction of the signal we are getting. So if we at this point, you would get a very small, if you put a cut on, let's say 1.1, you would get a very small fraction of the signal, but you would also get a very small fraction of the background. Typically, we plot the signal fraction we get, which is a very small number, somewhere here, and we plot the inverse of the background we are getting. So it's a small number, but you get the inverse, so that becomes a big number. So that's one point. And we keep doing this. We'll keep moving. We'll have points, because once you move, you have a larger fraction of signal, right? So you can see the signal increasing. The background, it changes depending on the background. So we scan the whole range, and we do a very fine-grained scan. I'm just showing discrete steps, but we do this. And then we have this line. So I'll just do it real quickly once more. So you are essentially calculating what fraction of signal is left on the right side and what fraction of background is left. But for background, we do an inverse of that. And we keep doing this. We get this. So ignore the other line for the point. For the time being, we get this, right? So this is what we call a ROC curve. Now, how is this important? You can pick any point. You can say, oh, I want a 7th point where my signal efficiency is 70%. Then you can immediately say, what's your background rejection? How much background you would get? And when you do analysis in Atlas, we decide on specific working point depending on if we want very pure signal, then it would be like on the right. But you would also see that on the right, the signal efficiency is high, but also the background rejection is low. And also like you're getting, So you have to kind of optimize between what point you want to work on. That depends on your specific problem. If you have a signal with very low occurrence, low probability of happening, then you probably want to stay somewhere here. Because even though you're picking up background, you're at least picking up enough signal so that you can analyze. So ROC curves are super important, and we use that all the time in machine learning. We have one last component when we do analysis. We have uncertainties. You know what uncertainty is. You have done labs. You have statistical uncertainty because random fluctuations. And then you have like systematic uncertainty, which is essentially everything else, like the bias, bias in the measurement, instrumental issues, calibration issues, whatnot. Finally, everything together, we can claim a discovery. If we have a good signal to background discrimination method, we can control our uncertainties. And as we keep saying, it's not even like finding a needle in a haystack, it's like finding broken pieces of needles in a haystack, because as I said, you don't find the Higgs, you find the decay products of the Higgs. From that, you reconstruct the Higgs. So that's my very quick summary of everything we do in particle physics. And we can use machine learning in pretty much every single step. Of course, we won't have time to describe everything. So I'll focus on some specific things today and tomorrow. But before that, I think I'll very briefly introduce what machine learning is, or at least how we use it or how I understand it. So, and this is, we have now gone back to 1980s. This is not something very new. Let's say we have two variables. I plot one on x-axis, variable 1. I plot one on y-axis, variable 2. My red points, red squares are the signal, and the blue arrows are the background. And this is what we get from data, from simulation. Doesn't matter, we get this. You want to find how you would apply a cut on variable 2 and variable 1, so you keep the most amount of signal and you reject the most amount of background. And that's the whole game. If you can do it well in 2 dimensions, great. A lot of times, as we will see, we have to do it in many dimensions. That's the way. So how do you do it? If you are very naively, you can just draw like a square like this, right? So I start with this, I draw a square, which kind of separates signal background. Outside the square, you get mostly the signal. Mostly the background. Inside the square, you get most of the signal. But it's not perfect. You can see my signal is 1, 2, 3, 4 signal points are outside, and 1, 2, 3, 4, 5, 6 points are inside, background points inside. So it's not a perfect separation, but it's not too bad. And that's what people have done for many years. But who says you have to have like a straight line cut? Why can't you have a cut which is a function of x and y, which is like essentially mx plus c, right? Like a recursion of a line. And now if you do that, you have slightly better separation. You have less background inside the signal. You still have probably the same amount of signal points outside, but definitely you have less background in the signal. So you make progress. But who said it has to be a straight line? No one said that. So you can have a curved line and you have less background. Again, the way I do this thing, I still have the same amount of signal outside. So I'm still losing a bit of signal, but I'm getting purer and purer signal inside my thing, right? So that's awesome. So that's what we want to do. Now, humans, you and I, we can do this in 2 dimensions. You don't need any fancy computer telling you what to do. You can all do it. But what if I said, we are not only dealing with variable 1 and variable 2, we are dealing with 10 variables, 20 variables. We are dealing with 100 variables with each have a 4 momenta, so 400 numbers, or 400 of these variables. No one, I mean, at least I can't see well in 3 dimensions when I'm trying to distinguish, draw this line. So this thing is called a decision boundary, and finding a decision boundary is hard. If you have like n dimension, where n is it doesn't have to be a super large number, even in 5. Can you see in 5 dimensions? No, I can't. I mean, so that's where we have to depend on computer algorithms. And as I said, people have been doing this since the 80s and 90s. This is something which is, I think, broadly classified as machine learning, but this is not new. We are doing this because otherwise we won't find our physics, and it's not new. Now, typically, this is, I just picked some random thing, but you have a lot of variables. Here, I think I draw the signal in red, the background in blue, like before. Lots of variables, they're distributed. And some of them, I mean, for example, this one looks quite nice. There's a nice peak in signal, a nice separation in the background. But this one, is very similar. This one, very similar. This one is different. This one is somewhat different. But we want to use each of these graphs, each of these distributions, and combine them to form an n-dimensional decision boundary. And that's what we are trying to do. Now, this is what we call MVA, multivariate analysis, which is you're using n variables in classification. These are called feature variables. I'm just throwing in some names because we're going to use it as we go along. Now, there are cases where these variables are correlated. And maybe these and these variables are very correlated. So we might be able to use one because we probably don't gain, if there's 100% correlation, we don't gain any extra information using both. So that reduces dimensionality, which is always good. Because at the end of the day, remember, computers are dumb. They do only thing you ask them to do. So if you make their job easier, then it runs faster, takes less memory, everyone is happy. So as I said, n-dimensional decision boundary is essentially n-dimensional surface. Just like a two-dimensional decision boundary is a line, a three-dimensional decision boundary is like a surface. So it's an n-dimensional surface. And then you just decide a cut on this surface, in n-dimensional surface, and then one side would be signal, the other side would be background. Now, as I said, you can start with the form momentum of every single particle that's coming in a collision. No one prevents you from doing that. And whether we like it or not, people do it. I mean, I remember going to conferences and people showing our rival collaboration, CMS, showing their results, and they use like 600 form momentums for like 600 individual variables corresponding to 150 particles for momentum in their machine learning algorithm. And then we are like, sure, you can do that. It's not illegal. But do you want to do it? I mean, on a highway, you can drive at 50 kilometers an hour if the speed limit is 80, or 100. It's not illegal, but would you do it? Would it make your life easier? You can go at 90, you can go at 110. So we would rather try to form variables which combines information, and which is also because we are physicists. I mean, I'm a physicist, so I try to find variables which would reduce the dimensionality of the problem and would make me understand. So for example, mass, sometimes we scale the variables by the center of mass energy because that scales well. So we do these things. So what is machine learning? We want to algorithmically find the decision boundary based on data. We can't program explicitly for every scenario, but that defeats the whole point of the exercise. So machine learning for me is essentially an algorithm which would, given a set of signal and background events, would automatically find the decision boundary. So why you call it learning? Because it can't do it in one step. You tell it, okay, I mean, I'm starting very simple. We'll go into more complicated scenarios. You give it labeled events. These are signal. So the algorithm kind of learns how signal looks like and how background looks like, and represent them by some functional form. Now, this is very, very important. Whether or not that functional form is realistic is immaterial. It's something the algorithm would come up with to represent this particular data set. It may or may not have an inherent functional form like that. It doesn't matter. It tries to guess the best functional form. The best machine learning algorithm is which gets the best functional form. And then use this functional form using the input variables, and then it tries to have an output variable which says, if the functional form is more like, if the data points are more like this inside the decision boundary, then it's signal. If it's outside, it's background. And that part is learning, trying to find, again, we'll give examples as we go along, not today, but tomorrow. But the idea is the machine needs to find, the algorithm needs to come up with this best functional form. And that's learning. That's learning based on labeled data set to start off with. And then when it learns, if you give it a similar data set, not the same one, then it should be able to do a signal background discrimination of this unknown data set, which is not labeled. That's the whole idea. Okay, maybe I'll just do this. Okay, I'll just do 5 more minutes. So the simplest one is what we call a decision tree. And this is for classifications. And the idea is like this. So let's say we have events, and we are trying to find if there is a Z boson, which decays to an electron-positron pair. Very simple. So we start off with, and this is how we can represent it by a flowchart. We take events. Do we have electrons which have opposite charge? Yes or no? If it's no, you assign a score of 0. Then you calculate the invariant mass. That's why I explained it. Is that number close to the Z mass? You pick the window. Typically, it's not exactly that because of experimental and theoretical limitations. So the Z boson mass is 90 GeV. If you get something like 80 GeV, you'd be half fine. If it's not within that window, 0. If it's within the window, then typically if you have Z bosons produced with very low energy, then the electrons kind of are back to back because energy momentum conservation. Are they back to back? Yes. So if this satisfies all 3, and this is a very simple case, then you say it's 1. So why it's called a tree? I mean, of course, it looks like a tree. Now, in this case, it's pretty straightforward. There are 3 conditions, and we kind of know in a physics way which is the order we would do. But for a new problem, you may not know the order, and each node, so each of these is a node, it corresponds to a selection, right? We decided if you are going with Y or going with no. So each node is a selection. Now we can try by different orders. We can vary these orders. We can try this first. We can try this one first. We can add extra nodes, all of these things. And or we can just take out one node and we can see if the classification performance improves. By that, what do you mean? If we can get more fraction of signal, less fraction of background, by whatever. And we try it many times. Now, of course, for a three node, it's easy. You can probably do it manually, doesn't matter. But if there are like lots of permutations combinations, like this is just a random schematic example, then you try to do it by a machine. You try to have a computer doing it for you, changing things, recalculating, changing things, recalculating. And then you would see like what combination works the best. So that's, in a nutshell, is very simple machine learning, essentially a decision tree. Of course, we can do more, like define more complicated thing. We define a cost function at each node, which is essentially what is the correct fraction of inputs which are classified correctly. So we want to have the sum of the cost function, and where the cost function is the lowest, which essentially means the classification is the best. And then, of course, that means the higher nodes are more important than the lower nodes. And you do all it programmatically, and that's machine learning. So I think, yeah, I'll end with this. So one thing we have to be careful about, if we showed this plot before, right? We have this like rectangular decision boundary. This is in machine learning terms we call underfitting, because this is clearly not the best. As we saw, we can do this, which is much better. So this is what we call underfitting. So if your algorithm, be it a tree, be it a neural network, which you're going to discuss tomorrow, not tomorrow, next week, if it does that, it's underfitting. This is not the best. But also, for this particular problem, I can come up with a decision boundary like this, which is almost perfect. I mean, I rejected everything except one background point, and I in fact included this signal point as well. This is great, right? Perfect. Best we can do. I could have also done that, I guess, even better. But is it good? No, because that's what we call overfitting. Because then we are tailored very specifically to this particular data set, the intricacies of this set. So when someone gives you a set which is similar, but not same, and we are so much dependent on this like tiny fluctuations of this one, for the next set, we are not going to perform as well. So that's the problem. So that's what we call overfitting. And as a physicist, I think this is what I'm going to leave you with this week. We have to kind of, and this is a paradigm we have been discussing in the community, what we call the difference between, or the important thing between deep learning, which is essentially in a nutshell these machine learning, AI kind of things, versus deep thinking. Because your brain is a computer. It is very, very powerful. How can you think ways where you can do the physics and then use these computers, because you can't see in 10 dimensions. So sure, use the algorithms, but use it sensibly. You don't blindly feed in everything you can think of, rather than you feed sensible variables so that your computer, your algorithm performs the best. So I think that's where I'm going to end, because I do want to take some questions if people want. And we'll continue with neural networks and then applications in some of the cases we have shown next Tuesday. Thank you.
Yeah, thank you very much, Deepak, for a very, very nice introduction to the topic. I don't see yet any questions in the Q&A, but maybe our participants need just a minute or two to collect their thoughts and ask them. I don't know if Bruce and Ilya would like to make a comment in the meantime while the participants think about potential questions. Okay, they don't seem to have questions.
Everything was very clear. Everyone understood everything.
Yeah, no, it was a very nice, very nice and clear introduction. Maybe Deepak, would you like, since this is the first lecture, and you mentioned a few times the practicals at the end of the course, yeah, would you maybe want to quickly review with the participants the software that they will need to install so that they are ready when they need it?
Bruce, Xifeng connected. I think he's the best person to do it.
Yeah, he's connected, but I think he is in the list of attendees. Maybe he should be moved to panelists. I don't know if they can talk.
Yes. I can make a plan. Let me see if I can find him. Maybe he used the wrong link. Where is he? Here we go. Here we go. Now he's coming. He should pop up.
Xifeng is the best person because he prepared the tutorial. So I think that
here he is. Yeah.
Hello?
Yeah. Hello.
Hi. Could anyone just remind me that situation?
Sorry. We just wanted to ask you, since this is the first lecture in the school, and you are in charge of the practicals, and I remember on the announcement we asked the students to install a few software packages. Would you maybe kindly remind the participants what they have to do so that when you start the practicals, everybody is ready and we don't just do, I know it's on the announcement, but from two sources is better than from no source. Yeah.
Okay, let me see. So basically you just need to do only one thing. It's just to install this, what is the name of that? It's Anaconda, right? Anaconda, yeah. It's just go to the website list there, and you download the package and you install. That's it. Perfect. And other things we can introduce during the hands-on session. So before that, you just install it and make sure you can open it. I can see your interface and not crashing. That's all. Okay, perfect. So that doesn't sound too wild. But there are some details because for different platforms like Windows, Mac, and Linux, possibly slightly different. I only have the experience of the Mac. I don't have Windows machine. So just make sure that you spend some time to figure out if you can install that properly. Usually it's fine. 95% is fine. In case some special cases, yeah. No, that's why I wanted to mention it so that people don't start panicking in the next lecture. and now they have a few weeks to sort it out. Yeah, but probably most people have Anaconda installed anyway, I would imagine. I think that's the only thing you need to do. You don't need to install a chain of the package, just one thing.
Yeah. No, perfect. Excellent. Thank you very much, Xifeng. We are really looking forward to your lectures at the end of the month. Fantastic. Yeah. Okay, I still don't see any question.
Students are welcome to email me if they have questions. My email is very easy to find, but it's just my first name dot my last name at cern.ch or wits.ac.za. I mean, you can Google my name, you will find my email. So I'm happy to answer questions by email. Or if you collect some questions for next week, that's fine as well.
Perfect. That we can also do. That people can maybe share their questions at the beginning of next time, or email us, and we will forward them to you. Yeah. Yeah, no, this is just the problem with this online thing, that it's if people don't collaborate, it's very difficult to engage. Yeah, but this was just the beginning, and I'm sure that people will start digesting what you shared with them today, and maybe start playing around a little bit, so that next time they will have more questions. Yeah, because I know just by browsing the names of the participants that there are some people that I know they should have questions, but maybe they're just shy. Yeah. Okay, fantastic. Then if there are no questions at the moment, thank you very much, Deepak, for the very nice lecture. Thank you, Bruce, and thank you, Xifeng and Ilya as well. And we will continue then next week on Tuesday at 2 p.m. again. And the link is the same for the participants. And yeah, and I'm really looking forward to see how the story develops. So thank you very much again. Yeah, thank you.
Thank you.
Thank you very much. Bye. Bye-bye.